this talk, so I'm highly hopeful that somebody in the audience will come up to me at dinner and say, Bruce, remember that question you asked? So this is a result of Yang's. After she saw Han's paper. And basically, you now look at all M is a set of ordered trees, like matrices. Okay, so ordered means just that I give the children of a vertex an order from left to right. But if it only has one child, it's just the child. It's not the left child or the right child. It's just a child. And you're going to let M be just some parameter variable of your choosing. And then you give a weight to each tree, ordered tree, by taking the product over all its vertices of M choose C sub V, where C sub V is the number of children. Right, so this is just a polynomial in M, right? Because it's, right, you multiply out the top, that gives you the polynomial, and you've got CV factorial on the bottom, which is just. So then Yang's here will look like this. If we now sum over all ordered trees, the weight of the tree, times the product vertices M. Now, we have no reason to believe that this is anything more than a rational function of M, right? Because we've got M's in the numerator for the weight and M's in the denominator, and well, it is a rational function of M, but it doesn't have any M's in it when you do quick cancellation. It is 1 over n factorial. So all the M's cancel, everything, you know, amazing simplification, and you get this. Again, you can use either my algorithm or the Tiefenbrook-Grabner algorithm to prove this, and it gives you back the binary case. How does it give you back the binary case? Well, you might expect that the binary case would be n equals 2, right? Especially because you've got m to the hd minus 1, and it is, because think about it. What happens if I say n equals 2? Well, then what is this strange m choose CV? Well, m choose CV is equal to 2 choose CV, and I claim that's just a number of ways to make the children of V binary. What do I mean by that? Well, I'll do it by example. What happens if there are no children? Well, then clearly this is 1, and of course if you've got no children, you've got a leaf and there's nothing to do. A leaf isn't the same in a binary tree and an ordinary tree. So there's no choices there. What happens if you've got 1 child? Well, then this thing is 2 choose 1, which is 2. And remember, if I've got an ordered tree, right, in the ordered case, if I've got a child, it's just a child. So in order to make it binary, I've got to make a 2-way decision. I've either got to make it a left child or a right child. So there are 2 possible ways if I've got 1 child. What if I have 2 children? Well, then this is 2 choose 2, which is, and of course that's also correct because if I've got 2 children, they're left and right in both the ordered and the binary case. And what happens if I get larger than that? Well, then this clearly is 0, which is what we want, right? Because if I've got 3 or more children on my ordered tree, it's going to be very hard to make it binary. Right? So that means when I take the product of all these, that's just going to say, look at each vertex, make it into binary, and then what you're going to end up with? You're going to end up with a binary tree. So wait. binary, and you're back into the case. So finally, the big one. What's the open question? Well, I've been calling these things hook lengths for no reason that is obvious from the tree case. But what it turns out is that, as I said, this formula is the original hook length formula. It comes from other contexts. So, I don't remember what number I'm up to. You will do with this point. So, the original hook length formula wasn't for trees, or that wasn't what it was called when it was used for trees. So the original hook length formula was for things called standard Young tableau. I don't think I have enough time left to define exactly what these things are. But let me just give you a general idea, and I'll be more than happy to talk over dinner with somebody who wants the precise definition. There are certain arrays of numbers that have increasing conditions, just like we had on the trees. And then in these arrays of numbers, you define things which are hook lengths, which actually look like hooks. They're these little angle things. And exactly the same formula, n factorial over the product of the hook lengths, holds. And there's this original probabilistic proof that I mentioned, due to Green, House, and Wolf. Probably the nicest proof of that formula that exists. I have no idea what even the analog of either of Hahn's formulas are for the standard Young tableau case. So the question is, find an analog of Hahn's formulas. So what I mean by that is you're going to want some sum over tableau, the product of 1 over the book lengths, which we already know what they are for these tableau, and then some expression that involves, oh, I forgot to say this way back at the beginning. The other really interesting thing about Hahn's formula, aside from the fact that it simplifies so well, is that it's the first formula that I know of that has these hook lengths appearing as exponents. All the other hook lengths formulas that came before that involved them only had hook lengths in the base. But now we're getting hook lengths in these exponents of 2. That was a new and strange and different thing for these formulas. So what I would like is an analog of Hahn's formulas for tableau. So we're going to have the hook lengths, and then you're going to have some exponentials that also depend upon the hook lengths, and they should sum up to 1 over n factorial. And I'll be bored, pardon my French, if I can find such a formula. And once I've found it, of course, I'd like a proof. So thank you so much for listening. You learned something.
Thank you. Of course, we'll be glad to answer questions in private and during dinner.